Hi, my name is Antonio Guillén, PhD student at the Polytechnic University of Cartagena, Spain, and I'm going to show you my article called RAIM, Reinforced Autonomous Intersection Management, aim based on multi-agent deep reinforcement learning. Autonomous intersection management can be considered as a traffic agent that assigns autonomous vehicles the right of way at the intersection to control the flow of vehicles, eliminate accidents, and reduce waiting time. These aims have traditionally been developed from simple algorithms unable to adapt to new situations and act in advance. The main problem with these approaches is the incapacity to adapt to new situations and to act proactively, as well as the possibility of obtaining adverse results in certain situations, as detailed in other works. Thanks to the progress in deep reinforcement learning achieved in recent years by teams such as DeepMind, Google, Facebook, or OpenAI, it was decided to propose a new aim based on multi-agent deep reinforcement learning. In the humble opinion of the authors, this is the first work that proposed the use of multi-agent deep reinforcement learning for the control of autonomous vehicles at intersection as a whole through an AIM system. The proposed system makes use of reinforced learning as well as other artificial intelligence techniques and was named Reinforced AIM, RAIM. RAIM leaves aside the traditional approaches and addresses the problem with a single controller that decides at any given time what speed each vehicle must carry within the intersection, considering up to 31 additional vehicles. RAIM has an egocentric policy. This means that in each time step, the speed that each vehicle must carry is calculated in an egocentric way. For example, in this time step, first, the speed that the red vehicle A must carry is calculated, which acts as an ego vehicle, placing its characteristic in the first neurons. The rest of vehicles place their characteristics in the rest of the neurons and are completed with 0 when there are no more vehicles. After calculating the speed that A must carry, the speed of B is calculated placing B in the first neurons, that is, B acting as an ego vehicle, and placing the rest of vehicle A, C, and D in the rest of neurons. In this way, the speed of all vehicles is calculated each time step. The characteristics used for each vehicle are detailed in this table, and the controller was composed of 4 fully connected layers, detailed in this image. The output neuron predicted the speed at which the ego vehicle must follow during the next time step. The controller was optimized through GD3 using PEAR as a method to sample the replay buffer and a curriculum training through self-play, where when stability in the result was reached, the simulated vehicle flow was increased. The simulator used was Sumo, a microscopic simulator where each vehicle is explicitly simulated. In addition, Python 3.7, PyTorch 1.5, a RISC processor, and a NVIDIA graphic card were used. Two different scenarios were used, one as a training scenario, another as a test scenario, in order to compare RAIM with other control algorithms developed. The training result showed the convergence of RAIM through self-play curriculum learning. It can be seen how, when the flow is increased, there are convergence in value. The results of the test scenario are shown in this table. The results show that RAIM is able to reduce travel time by about 50%, as well as a reduction of waiting time by 90% and a reduction of consumption for electric vehicles by 70%. These results are impressive and show that AIM has a great future coming. The development of this AIM based on reinforcement learning achieves more than those obtained by the previous developed AIM and provides a great advantage over the traditional techniques of traffic light control. The behavior of RAIM is shown in this video, which can also be found through this YouTube link. Finally, thanks to the use of reinforcement learning, RAIM has been able to obtain amazing results, being able to reduce the waiting time by more than 96% and reduce the electric power consumption up to 66%. This shows that RAIM has a great potential for improvement compared to the proposed system, as well as numerous improvement paths, such as adding attention mechanism based on transformer or position prediction mechanism in order to be able to anticipate future states more accurately. Also, RAIM reached a very important achievement in reinforcement learning applied to real world.